colloquium, the first one this semester. We're very happy to have Professor Earlence Fernandes at UCSD, and before that we were at Fields at University of Wisconsin-Madison. And yeah, he works in security. Tell us more about some of the things. Also, I think you'll explain your computer marketer biography about hacking out.
Yes. I have towards the end something. Yeah. Okay, it's being recorded. Okay. Yeah. Thanks for that introduction. And I'm excited to visit here and talk about some of the stuff my students have been doing. And my goal is to kind of convey kind of a viewpoint, an approach to computer security that I kind of share with my students. Okay. So let me try to, if I can switch slides, that is. Okay. So evolved computers are everywhere. They help us at home, they drive us around in vehicles, they even assist doctors. Now there are two hallmarks to these evolved computer systems. They are connected, they're embedded, and they're capable of learning. And second, they involve technologies at multiple layers of the stack, ranging from new kinds of physical processes right up to machine learning models. But the problem is that if these computers are going to be everywhere, then so are the attackers. And these attacks are no longer confined to the digital world, right? I mean, they can come through the physical world, and the attacks can have physical world impact. And so in this setting, computer security has this key goal of providing the benefits of all of these new technologies without the security and privacy risks. And to meet this new role, my vision is that security is really a whole system property where we formulate and tackle security problems in terms of end-to-end system design. Okay, so to match this whole system view, my approach to formulating and solving these problems is similarly end-to-end. First I will often threat model these emerging technologies and kind of just try to discover new types of attacks. And that's kind of a reference to the stop sign thing that Manoj mentioned. And kind of based on that, I will kind of formulate security principles by taking inspiration from classic ideas like least privilege and isolation. And this is kind of what I call applying the security mindset, and this is something we do a lot in our group. And then motivated by that, a lot of my time is spent kind of building systems, and in my experience, kind of this involves a range of techniques, applied cryptography, access control, PL, and today I'll talk about some of the applied crypto we've been doing. Now, beyond this, this is the kind of the primary research cycle, but beyond this, I think it is super important, if there are ways to impact society positively after this, it is very important to facilitate that as kind of researchers in academia. And for me, this broader engagement is kind of taken various forms. Open source is the classic thing, but then I do a lot of industry tech transfer, and also I consult with a lot of government agencies. Now, although this kind of, this helps me address these emerging problems, I think it is most impactful when they're applied to technologies that are about to widely become deployed, or those that have recently evolved. And so I've applied this way of approaching computer security to what I think are kind of significant evolutions in how we do computing. Smartphones was the whole thing. I've done work there. The Internet of Things is kind of this ongoing thing where we are changing how computing is done. I do work there. These internet scale automation tools and even kind of machine learning and security. So I kind of take this approach of computer security to all of these areas. So that's kind of just a big overview of what we do in our group in general. So today I just want to focus on one topic, and that's kind of this idea of tailored privilege in distributed systems. And in the last 5 minutes or so, I'll talk a bit about machine learning, because these days, if you don't talk about machine learning, people will be unhappy. So I will include that. Okay, so I'm going to jump in here. These are pictures of my students, between Wisconsin-Madison and UCSD that are kind of leading the effort here. Yeah. So the idea here is that there is a web API for everything, right? So you have your digital resources like email, health data, online storage, but then you also have physical resources like the devices in the home, devices in the buildings, industrial equipment, that kind of stuff. And so the idea here is cloud computing is now this commodity, and manufacturers are essentially putting all of this stuff online on the internet. And the hope is that by bringing all of this online, it will lead to new functionality, new efficiencies, and all of that. But the problem is they don't really talk with each other. They kind of exists in silos. And because of this, the main benefits of all the network connectivity is lost, and what we get is simply hackers hacking these devices. We don't get any of the actual claimed benefits of connecting all of this stuff to the internet. Now recently what has changed is that there is this class of distributed system called integration systems, and they function as kind of the substrate that connects all of these online services. Okay, and I'm going to refer to them as kind of these trigger action systems because of how they work. That, you have some kind of data producing service, it triggers a small program that runs in some cloud somewhere, and then it produces some action that's going to change the state of some device or some online service on the side here. Okay. And I'm going to use this as kind of an application area for exploring this problem of tailored privilege in distributed systems, and I'm going to kind of define that as we get more into the talk. But just to give you a sense of what I mean, like here are some example trigger action programs. The interesting thing is that software engineers are not writing these things. They're just regular users who have bought these devices, who have accounts on these services. They are kind of clicking and dragging and creating these small programs. If there's too much stuff in the air in the room, then turn on the air purifier, or if something weird happens with my PayPal, weird transaction between 10 and 6, then send me some kind of warning and stuff. And so you have these small programs that have privilege to all of these other resources of the user, and they're kind of running and creating this kind of interesting functionality. Now under the hood, what enables all of this is a control sharing protocol like OAuth, right? So let's say that the user wants a program, hey, turn off the smoke detector, turn off the oven if the smoke detector goes off. What's going to happen is this cloud service here is going to negotiate 2 OAuth tokens, the gold coins there, and those tokens give that platform the power to interact with these resources, like detect if there is smoke, turn off the oven, whatever, right? Now the thing to realize here is that that service is very large scale. Okay, so like think millions of such programs, millions of such users, millions of resources. With something like OAuth, all of the power to interact and change these resources is in those tokens, and they're sitting in this cloud service. Okay? Now, applying the security mindset, that's not too great, right? Like, this is just the cloud service, right? Cloud services get hacked all the time. What if the tokens are leaked? And what's going to happen then? Right? An attacker could get access to these tokens and then kind of do whatever they want, right? I mean, they do not have to execute that program. They can just do whatever they want. And so, the first question here was, we need to understand just how powerful these tokens are. What does the word access mean, right? Because no one tells you, none of these cloud services are going to tell you, like, okay, access means X and Y, like you can execute function or API A and B. Right? They're not going to tell you that. So we need to somehow study this experimentally, do some kind of measurement. Okay, so we analyze what access means in these real systems, and we did a bunch of measurements. I'm not going to get into details of that, not super interesting, but happy to talk about it. But the biggest finding is that these credentials are overprivileged, meaning that they can do a lot more than what they are supposed to do. So for example, say that the user has a program, if I upload a file to Google Drive, do X, right? So it needs access to that new file, but it turns out it can do stuff in the red as well, like such as share that file with who knows whom and delete those files. Okay. Now logically, the minimum privilege that program needs is to just access the new file. Right? The rest of it is irrelevant. Why does it need access to all of that? So this is one example. We did a larger study. So like this kind of represents the result of that measurement of what access means. And so the x-axis here is a selection of kind of endpoint services, and the y-axis is account. And these red hatched pieces are essentially APIs that the tokens give the bearer access to. So whoever has the token can execute these APIs. But the interesting thing is that the user cannot actually ever write a program involving these APIs. There is simply no way for them to do that. So this is like pure overprivilege in the sense that not even the user can execute these functions. But if you're an attacker, you get this token, you can just programmatically call that API and do bad stuff. Right? And so clearly, if the user cannot ever write a program involving those APIs, then by definition, it is overprivileged. Yeah? So that's pretty bad. And kind of not surprising that Facebook is a big outlier there, but it is what it is. Okay, so that sounds pretty bad, right? Now, but the security mindset teaches us to ask further, okay, that sounds bad theoretically, but is this bad in real life? Is this exploitable? Okay, and so what we did was we used a bunch of known techniques to hack real trigger action services, such as if this then that. It's like one of the popular ones with millions of users, and to kind of demonstrated proof of concept attacks of what can go wrong if one were to leak these tokens. So for example, we were able to, this is some kind of IoT chip. Using the token, we can reprogram its firmware. We can delete people's Google Drive files. We can power cycle smart home. We can smart home device. We can do many things. And of course, the caveat here is that we did not actually hack random users. We just hacked our own accounts. So that's super important. You don't want to be hacking people's accounts and get in jail or something like that. So, but it's not only a matter of the cloud service getting hacked, right? I mean, here is IFT's privacy policy. So if this then that is kind of like one of the popular trigger action systems, and they just say there, like, for whoever cares to read a privacy policy, they say, I mean, we're going to take your personal data and we're going to give it to some people. And that's what they're going to do. And they're pretty open about it. And some endpoint services like Gmail, it used to integrate with these things. Then they kind of got spooked. They're saying, okay, this is not super good from a privacy standpoint. We're going to kind of pull back support. And we're not going to integrate with these things. And this is kind of unfortunate, right? Because control sharing of all of this information is kind of a fundamental tool for making use of all our stuff online. Otherwise, it kind of defeats the point. And so as I mentioned, my vision is to kind of secure these evolving systems. And so the question is, how can we make all of these problems go away while still allowing this kind of useful functionality to occur? Okay. By the way, I don't know what the protocol for questions is. Feel free to interrupt me. Always happy to take questions at any point. Okay, so now this is kind of the problem setup. Okay, we want to secure this kind of distributed system. We want to secure these tokens. We want to prevent them from being misused.
Previous slide, when you say power cycle, the last use case.
Yes. Power cycle means you just turn it on and turn it off, and keep repeating that on and off, on and off, on and off.
Is it like draining to a battery or what?
You can destroy the device. So it's like if it's like a large like a AC or an oven, you can just create trouble. Yeah, it's just start toggling. I mean, you can do many other things. We just thought this would be kind of annoying to users. So technically, the token allows you to turn it on and off, and so we just chained it together. Yes. Okay. So how do we solve this, right? And so here are a few potential solutions, right? I can have really short-lived credentials, right? So the whoever is minting the token can just mint it for a few seconds, and then the person using the token has to come back and get a new token through some kind of refresh procedure. Okay? And so the idea is that if someone detects that the tokens have leaked, then you just stop honoring refreshes on the old tokens, and you just require everyone to use a new thing. Now, but this kind of depends on timely detection that something has gone wrong. And in real life, attackers have been in networks for days and months without anyone knowing what has happened. So that's not, it's not a very satisfying solution. Right? I could have super fine-grained tokens, right? So instead of having one token that can do many things, the one token does a very specific thing. Now that's okay, but then again, this is a large-scale system, right? I mean, you have millions of users running all kinds of programs. Over time, you're still amassing a lot of power in the tokens, and if all of them get leaked, you're kind of back to where we are, right? So none of these really kind of solve the problem, and at times like this, what I advise my students to do is kind of take a step back and kind of abstract the problem.
So how bad would it be to only allow a token to be used only once?
Like use a token once?
One time?
Yeah. So I mean, you could do that and then require them to get a new token. But then something has to make a decision that, whether I should give a new token or not, whether the state of the system is secure or not. And answering that question is very difficult. Like, how do you know, like in this large scale system, everything is okay or not?
Would it be feasible to tie the tokens with the program that's involved?
Yes, so that's where it's going. So that's a good observation. We're going to try to tie the use of the token with the program and kind of convert the program as almost a policy on the token. So that's kind of where I'm trying to head this to. But that's a good point, yes. Both are good points. So what's the fundamental problem here, right? Why do we have this design level overprivilege? Right? So what we have fundamentally is some kind of API server. It's protecting some resources, and what it's doing, it's using this standard OAuth protocol to give tokens out to people. Now the thing is, this privilege of this token does not align with what the third party needs, right? And why is this the case? It's because these services are built by different people, right? Like Samsung builds devices and then it'll build an API. Your Google Mail builds an API. Your WeChat or Zoom, whatever, builds an API. These are separate things, right? They do not necessarily know about each other, and they just decide their API methods, and they decide some kind of mapping between APIs and tokens. Now the users are writing these programs that interface all of this stuff together. You're naturally going to get this mismatch here, right? Because they were not originally designed to interoperate, and nor can they be, because there are so many services on the internet. They're never going to be able to talk to each other and negotiate a token that is exactly the thing that I need. Like exactly I need only to turn on the oven only at 9 a.m. or exactly just access the email subject line only if there's the word confidential in it. You're never going to get that kind of fine-grained privilege. So now the textbook is going to say, okay, yeah, just do least privilege, right? I mean, that's kind of the standard idea, like from the 70s. Every program, every user of the system is going to operate using the least set of privileges necessary to complete the job. Okay, so this is good on paper, right? And it's super simple. But the thing is, it's very challenging in real life, because it's kind of hard to pin down like what exactly is this job that is being completed, right? And while I'm doing that, like what is the effect of this least privilege on other systems things that I care about, like performance, functionality, usability, right? What is the effect of this least privilege on that? So rather than sticking to this, this rigid textbook definition of least privilege, I'm going to claim we need this thing called tailored privilege, where the idea is that it's more flexible than least privilege, because it can hit concrete trade-offs in all of these other kind of dimensions that we care about. Okay? And I'm going to offer several definitions, concrete definitions of what I mean by tailored privilege. Okay? So that's kind of what my students and I are doing. One of the big threads is kind of exploring concrete meanings of tailored privilege. And so one example is that it allows a token bearer to execute a specific operation only if there is some kind of proof involving the state of a distributed system, okay, in terms of some kind of Boolean predicates. Another example might be that it allows some operation using the token only if that operation is a result of some kind of trusted program execution. Okay? Or the token can only be used to access minimized data for some definition of minimal. Okay? And so these are kind of papers that explore these ideas. And today I just want to kind of go in detail in this one idea of almost like the idea of attaching a program that governs the use of the token. We want to attach that to the token. Okay. So I'm going to use a running example here. This is the PayPal thing. It's running some kind of simple computation on the sensitive data. Doesn't matter what that is right now, but it's doing something interesting there. Okay. So why is this a good example? Why is this a good area to explore tailored privilege? There are two reasons. First, the user has already kind of told us what they want the third party to do with privileged access to their resources. Now, in general, this is a very hard problem to understand the user's intent, like what they want the third party to do with privileged access to their stuff. But here they have given us kind of this nice little program that says, hey, this is kind of the stuff I want you to do. I don't want you to do anything less or more than this. Okay, so that's kind of a nice playground. The second thing is like this language that expresses the user's intent is actually fairly well defined and simple. And this kind of will become relevant once we get into some of the crypto we're using, because we have to kind of translate this into some circuit language. So these two insights kind of make it, it's simple enough, but it's, people still use it, and you can still kind of work with it and get guarantees. Okay. So at a high level, what we're going to do is we're going to require all of the resources to operate on encrypted data. So the PayPal is going to send out some encrypted transaction data to this untrusted thing in the cloud. This thing is going to run a computation and then send out some results of encrypted evaluation. Okay. But the thing to note is that this is not a TLS. There's not two TLS connections there. That is actually end-to-end encrypted. Okay. So this thing is going to run on. We're going to run this computation on encrypted data. Okay. Now, why is this Taylor privilege? Because if you think about it conceptually, what we are getting is this guarantee that whoever has the token, they are bound by this garbled circuit that we are going to attach to the token. So the token gives access to some data or gives the ability to execute some API on some resource on the internet. Those arguments, that data that is being pushed into the use of the token, that can only be produced by a valid execution of a garbled circuit. Okay, and I don't know how familiar y'all are with. I mean, I've met some of y'all who do crypto, but garbled circuit is one very elegant way to compute on encrypted data. There are many ways to do it. Since we are building kind of real large-scale systems here, this turns out to be one of the more efficient constructions out there. Okay. And so, again, in your mind, conceptually think that, earlier used to give people tokens, and then that was it. The token itself kind of embodies the power to execute these operations however the bearer wants. Now we're going to give a token and we're going to attach a circuit, and now the third party is bound by this circuit. All they can do is manipulate the data using that circuit, or they can deny. Okay, so there's two options.
So the circuit is a one-time thing. Right?
Yes.
So we'll have to do every time.
Yes. So we have one solution for that. That turns out it was one of, like, in this whole project, that's one part that I don't like. Like, it induces this producer-consumer pattern between someone who is trusted, who generates the circuit, and then the untrusted evaluator. And I'll talk about how we solve that in the system. I mean, we don't really make it reusable. You just need multiple circuits for multiple invocations. There is some theoretical construction for using it, but then that depends on a lot of other stuff that's not going to be real. So I'm going to establish a little terminology to make it kind of simple. So I'm just going to replace that predicate with this boolean f1. And then I'm going to replace that transform with f2. Okay, just to make it a little more manageable. Okay. So now, with that in mind, let's think about what we mean by security here, right? A little more formally. So like, what I'm going to do is as a proxy for all of the threats of the credentials have been leaked, or this has a bad privacy policy, or it's been hacked, or whatever. I'm just going to say that it's malicious. Okay, I'm going to kind of catch all, just say I don't trust it at all. Okay, but I still wanted to run these kind of programs at large scale. So yes, so you can have multiple trigger services. I'm just trying to simplify it with one triggering. This was kind of the original design of the system, and then like IFT and all these companies kind of evolved, and they said, okay, now we want multiple triggers, and so there's a way to extend the protocol to multiple things. So I'm going to say it's malicious, and so what that means is that I don't want the attacker there to learn the trigger and action data, right? Obviously. I also want an integrity guarantee. They cannot manipulate the computation, right? So whatever this result of F2 is, they should not be able to change that. Okay. Now I'm going to assume these endpoints are honest but curious. Okay. Now this is okay because if they are compromised, then we don't have to worry about that, right? I mean, your Samsung, LG, Google is already hacked, and then you have bigger problems on your hand. Addressing their trustworthiness is a separate, whole separate set of things. Now, in that setting, I don't want the action service to learn the trigger data in its pristine form, okay? Because that's not what happens today, right? Today, the action service only learns the trigger data, which is the transformation according to F2, and only if the condition is true. Otherwise, it doesn't learn the trigger data. And so, this is a classic principle. If I'm building security, I do not want to reduce the guarantees that I have today. The other thing is that it should be able to run this without learning the truth of that predicate there, right? So this guy cannot learn whether F1 is true or false, right? Because we want it to be totally oblivious to what is going on in there.
So, what we write this if then and implement an arbitrary F of trigger data.
So this could be like this is an arbitrary boolean, and this is just.
Yes, and we even need F. Just be,
Do you need the if then?
it's just some function of trigger data. It takes trigger data.
Yes,
gives
yes, in general, yes. Yes, in general. But this kind of simplifies and shows a little more structure. In general, you can just say, okay, that's some f of trigger data. Okay, and so then from a systems perspective, again, we are doing tailored privilege here, so I need to be very conscious about how I'm changing the system here. So I do not want to change the trigger and action service. Okay, like, they are kind of these RESTful web services, and they, to the maximum extent possible, they should remain that way. Okay, and I do not want to make them aware of each other, right? I mean, I do not want Samsung to be aware of like Google or whatever. Pick your pair, and I do not want them to have any concept of this program here, because they don't. I mean, they are just providing APIs, and that's all they should be doing. Okay, so I cannot do anything there. Right? So those are constraints. Now, an immediate problem here is that if this thing is malicious, how am I going to even create programs in the first place? Right? If I trust that thing to, I tell it, here's my program, it can just manipulate the program and say, this is your program. Right? So how am I going to do this? So what we do is we kind of, distribute trust. So right now it's a centralized trust model. Everyone trusts that one cloud service. What we're going to do is like, everyone has a smartphone and laptop. We are going to say that, okay, you trust your smartphone or your laptop. You're going to program these, create these programs on your smartphone, and then we're going to do stuff to it, and then you transmit that to the cloud service. Okay, and so the idea is that you do not trust the cloud service anymore. You just trust that your device has not been hacked, okay? and everyone trusts only their device. Okay, and this is a big change from what we have today, because all it takes now is one hack here and you're done, whereas now the attacker has to go and hack multiple devices to get the same kind of security material that they were robbing from the trigger action service.
Again, aside, but so if they update the app, you're already using some app.
Right.
So you're expecting that the app will be built by some other.
Yes, exactly. So it's like the analog would be like the TLS protocol, right? I mean, you have servers and clients, and as long as they agree to the protocol, you can keep updating these apps. So as long as they adhere to our protocol here, they can independently update the two components. But yeah, that's a very good point. Okay, so this is kind of a common idea. Like in all of the projects we're working on, we kind of use the same idea of like we're going to have this root of trust that only a user trusts themselves and no one else can. A distributed root of trust. Okay. Now here is kind of the high level overview. What's going to happen is that this trusted client is going to periodically garble this function. So I've simplified it even further here, right? Like what you said. It's going to garble these functions periodically, send them ahead of time to the cloud service. When there's a triggering event, the trigger service will garble that data, send it. This thing is going to pick one circuit, run an evaluation procedure, and send the garble results out to the action service. Okay, so that's kind of very high level. And so, kind of translating this to the standard kind of the MPC terminology, that functions as an honest generator. Those two parties kind of jointly play the role of an honest generator. These two parties play the role of the evaluator. Okay, and so now the trust is very asymmetrical here, and this is so this is not what you normally get in the MPC setting. You don't have this kind of asymmetric trust model, but we can do this because of how trigger action systems actually work. Right, this is a totally reasonable split of things to do. Right? And this is simply because the evaluator does not have any secret input, right? Normally the evaluator would also have, like in a classic 2PC setting, your evaluator would also have an input, but here it does not have an input, right? It's just running a functional input coming from somewhere else. Okay, and so because of this, what we don't need any OT, we don't need any oblivious transfer here, because that thing creates a circuit and it sends all the labels out here. this thing doesn't need labels corresponding to its input, right? So immediately there, just by design, we cut out all of the overhead that comes with OT protocol. We are just doing garbled evaluations in the cloud. This is garbled output.
Decoded one here.
It's decoded in this honest but curious entity.
Where do they get the keys for decoding from?
Yes, so I will show that, like the trusted client will do a kind of setup. But there are other challenges, right? So like, for example, you could convert anything into this into this garbled circuit language, but then, theoretically that's great, but then in real life it's not so great, because you can quickly blow up your circuit sizes depending on the complexity of what we are doing, right? And we want to run real programs. We don't want to be playing with toys here, so we want to do real things. And so it turns out that this whole trigger action programming paradigm is kind of interesting, because the functions are stateless. There's no concurrency, there are no system calls, they're kind of almost like pure functions. And those are kind of nice to work with when you try to convert them to these Boolean circuits. Okay. The next challenge is that we need to ensure that this thing does not forge these output labels, right? I mean, these are just random numbers here coming out. And if they're truly random, then they can just produce some other random numbers and then trick the action service, right? Now the way to do that would be to work in the malicious secure setting. Okay? But the thing is, those malicious secure protocols tend to be less efficient than the semi-honest case, right? And so that's one problem. The other problem is that it can introduce dependencies between services, and that's a big no-no, right? Because as I explained, from a systems perspective, these people do not need to know anything about each other. Right? So that's not great. Like, we can't just use a standard approach here. So what are we going to do, right? Because of this asymmetricity in the trust requirements, we can actually get away with using semi-honest garbled circuit evaluation if we put in a few tweaks, and I'll explain those tweaks. But because of this asymmetricity, we can actually get security against a malicious evaluator just using a semi-honest implementation. And that's very cool, I think, because now I'm getting the efficiency, right? I am consciously thinking about, okay, I want to build this thing as an efficient system, and I don't want to go to use the malicious secure part. And so the paper kind of has some theorems that prove that this kind of construction is secure.
That makes sense. Obviously, it's already authentication, right? Output tag and tag at the label at the output serves as an authentication.
Right.
So is that all you need, or do you need more than that?
You need to ensure that all of the labels, so this party needs to ensure that all of the labels coming from here are valid labels,
So
not.
they have got the decoding.
Yeah, so we do not want, so you could transfer the whole table to this, but then you have to keep doing that. That's a lot of information that you're transferring. So we have a kind of a trick to avoid that amount of.
The labels come.
Yes, we have a way to kind of almost like, you can think of it like we can regenerate, like we share actually a seed, like so you generate like seeds to create the labels. Because this is asymmetric, right? This is honest but curious, and only this is malicious. We can share that seed with the action service and then regenerate those labels on the action service, and then just compare them that have you gotten valid labels or not?
And the concept is completely prepared by the trustworthy.
Yes, the client. Yes. So I'll go into the protocol. The final thing is, all of this should happen without, this cannot know whether the predicate is true or not. It has to just be evaluating and sending data. Right? But this thing has to eventually know whether it's true or not. Okay, so here's how it works. So here's the setup, right? So in the beginning, this smartphone or whatever browser extension is going to generate two user-specific symmetric keys, KT and KA, and then it's going to distribute this into the user-specific account inside the trigger and action service. Okay. And the triggering key is used to generate the encoding table, and this is used to generate to protect the decoding table. Okay. But the encoding and decoding is produced by the trigger side. Okay. So here is how it works. So for the function garbling, ahead of time the user said, okay, I want a program that does X or whatever. Then we are going to convert that into a circuit, and then a few steps are going to happen. Okay. So this is a fairly standard step. You generate these two offsets. You can just think of them as kind of bit strings in the length of the security parameter of the system. So we had 128 bits. And you go into the usual GC process here to generate a circuit, and you get your circuit. And conceptually, you can think of it as stacking of those two, of the predicate and the transform. And so conceptually, we just have one function, as Manoj had pointed out. But then there is some interpretation to the wires, right? The first wire, we reserve it to be that kind of a label representing the predicate boolean. But of course, this is a random number. And these represent kind of the result of data transformation. Okay. So now we are going to add a few non-standard things to the output. Okay. The first thing is what we call decoding info, and that's basically a hash, just a regular hash of a concatenation of all of the zero labels of the data transformation outputs. Okay, so W1 to WM, right? So that's these ones, just the zero labels. Okay. And then we're going to add that offset ER, and it will become clear why I'm doing all these things. And then I'm going to encrypt that under this key. Okay, so a key which is like the action service key, and the true label of the predicate. Okay, so the L1 W0. Okay. I'm going to do that, and then I'm going to add an additional HMAC to this whole thing. So this is one part, and this is another part. I'm going to add an HMAC under KA. So again, the action service key of the false label of the predicate. Okay, so this is the true label. This is the false label of the predicate. Okay. Now these two additions are going to help me get security against a malicious circuit evaluator. I will show you that in a second. Right? So I'm going to do this. This kind of happens on your trusted device periodically. You're generating this blob, and you're kind of sending it to the trigger action platform, and it's storing it there. Okay? Now let's say I want to execute, like some data has come in. I'm going to execute. So the trigger service is going to first garble, right, using this KT. And fairly standard procedure, nothing interesting there. It's just going to garble that input data and produce that. Send it off to the tap. Tap is going to pick one garbled circuit from its set for this user and for this function. It's going to run a standard again evaluation procedure, nothing there, and then it's going to send that decoding blob as is that we had generated during a setup. Okay, and finally, again, fairly standard, using the decoding blob, they're going to decrypt that information and then run an ungarble procedure. Okay, so now coming to your question, why did we generate that key? Well, the action service wants to get access to the decoding info, right? So it has to somehow unpack that, right? It has to unpack that encryption there. Now, it gets some LW0 label, right, from the evaluation procedure. It will get some LW0 label. If it turns out that in fact it is the label representing true, then it will be able to form that key, and it will be able to open up that encryption and get access to the decoding info, right? So in this way, the action service is able to determine. No. Because those kinds of conditionals are generally hard to express in a GC. I mean, GC is like a combinational circuit. Yeah, I guess that's possible there. But then the tap, would the tap learn about?
Nobody will learn. Even you're zeroing out the output as the receiver will know that the output has been zeroed, which you are allowing it.
I see. I mean, that could be a valid way. I don't know. I'd have to think about that some more. But the idea is to kind of hide from the tab whether that statement was true, that predicate was true or not. Right. Okay. So we do it this way so that, for exactly that property that, if the condition is true, then you only get access to information to go further in the process. And so, but the thing is, like, we still need kind of integrity here, right? Like, this could have forged that LW0 label.
But yeah, that,
Yeah, so
that's
that's
part of the label that could be like half of
Yes.
the label could be
yes,
long.
right. And so the way we do it is we just simply include a HMAC there on the false label, and we just check, if this decryption has failed, did it fail because it was a 0 label, or did it fail because someone attempted forgery?
Yeah, because that kind of thing won't be there in the other cases.
Right.
Just get a label and if the Mac checks.
Right.
you
Right.
know,
Right.
So in terms of when the Mac is could be okay. Yeah, you want to only have the 1K that will be used. And what I was going to say was that the output label could be longer than the other labels.
Mm-hmm.
So one to 8 bits of Mac security, and we're only using 1 to 8 bits for the label. But still have 256 bits of the only the output.
Mhm.
You have to go inside and change the values.
Right. Exactly. Yeah, I guess that could be possible. Yeah, that would be interesting to check out. Yeah, that's a good point. So, using this mechanism, we are able to, check that, hey, the predicate was indeed true, and kind of check it robustly without any possibility of forgery. So that's okay. So now it gets this decoding table, and it can essentially do a ungarbling procedure, but we still need to ensure that the transformation labels are correct, like they are not been forged with. And so the way we do that is simply, the ER offset has been disclosed to action service, and this is safe because the action service is not a malicious entity, only the tap is a malicious entity. And so using that ER offset, we can actually reconstruct all of the 0 labels for this particular instance of the circuit. And then we just concatenate and make sure that it's exactly the same as what we expected. And so, that way we can know that they're not just generating some random labels and kind of tricking us to do that. Because, with the standard, with the simplest garbled circuit implementation, all of these would ungarble and give some data, it'd just be junk. Okay, so the final challenge is kind of, we want to support real programs, right? And so what we did was, we kind of did this empirical thing where we looked at, the top 500, we crawled this website, we looked at the programs, IFT and Zapier, and we kind of classified them in various types. Boolean arithmetic, fairly simple, but the interesting thing was string operations. Okay? Now this is not a super standard thing that you would, see with garbled circuits. At the time we did this, there was only one paper that you could find that did kind of string operations as Boolean circuits. And that had some assumptions that didn't work for us. So we built our own way to kind of encode DFAs as these Boolean circuits, and then do those limited set of string ops like contains, replace, extract, stuff like that. Okay. Again, this turned out to be quite interesting, but I don't have time to talk about it. But that's possibly kind of independently interesting from the system. Okay, so it turns out that once you do all this, you can you express all of these real programs and kind of make things work. Here are some statistics on the time and circuit size. Okay, this is not 100% because some of the Zapier programs were parsing HTML, and doing HTML parsing circuit is kind of very, very difficult. So we said we just not support it. Now beyond these macro benchmarks, here's what it looks kind of at a server level, right? So the latency is okay, is not a big deal. The x-axis is the kind of these selection of some programs, some operations, and the y-axis is either seconds or requests per second.
What circuit library?
We used the EMP toolkit. So it's a GC library written in C. So it's actually pretty good. It gives you a lot, because a lot of the GC libraries, they will kind of bake the OT into it and all of that stuff, and they will do line by line kind of work. We didn't need any of that, right? We just need kind of the GC part of it. EMP toolkit, yeah, that's pretty good. Pretty good. I'd recommend using that. So yeah, so latency is okay, but throughput is where we get hit. Like this is like I think like a 59% decrease. So like same server capacity, and you kind of you saturate. You send so many requests that you saturate, and then you get kind of this 59% decrease in throughut. Now that's not super nice, but still we are computing on encrypted data here. It's not the guarantee is fairly strong. But what does it mean kind of for an end user? Right? Like what does an end user experience in all of this? And so there have been some prior work on like kind of that kind of measure like what's the average number of programs people have and how often they run. And based on that we kind of estimated that your phone would spend 10 seconds a day generating these circuits, because again they are one-time use only. So your phone or your laptop has to given your programs, it has to look at them and generate ahead of time based on these estimations and then send them off to the trigger action service. This would be about 62 megs of data. So again, if you kind of compare this is like uploading about 25 HD photos or like a 1 minute HD video. So if you're you're doing like TikTok or Instagram or whatever, you can definitely be doing carbon circuits for your privacy, right? So but again, this is not super nice because if your phone gets disconnected or your laptop is disconnected for a day or whatever, then the whole thing just stops, right? Because then there are no circuits left, and then you can't run anything. So that's the big negative part of this system that I do not like. But that's what you get when you do GCs. We could have done homomorphic encryption, but then that thing is still is an order of magnitude slower than these circuits in our benchmarks, and on top of that we need some kind of proof of integrity that the computation was executed as intended and not manipulated somewhere in the middle. But still there is something interesting to look forward to in terms of future work here. Okay, so kind of stepping back here, so I've shown you one example of one interpretation, one definition of tailored privilege, and on this graph it has overhead, it has high overhead, we saw that concretely. But it provides fairly strong confidentiality and integrity guarantees. Okay. Now these various projects we have been doing kind of occupy different points in this space. I'll just briefly talk about that paper there at Usenix Security, and that kind of has the lowest overhead among all of this, but the guarantee is also kind of weaker compared to what I just talked about. Okay, so so here is the kind of the idea, right? So let's say this is the program. If the new email is there between 9 a.m. and 5 p.m., then send me a Slack notification with the subject line. Okay, and this is running there. Okay. Now, the trigger API, because of the power of the token and how they're designed, is going to release the subject line, but then it's going to release every other thing. On every new email, I'm going to send everything, right? Because that's how I've designed the email service is designed. Now, the question for you is, for the correct execution of this program, what minimum trigger data do I need so that it runs correctly? What's the minimum amount of data I need to make it happen? This is all the data it sends, and this is the program. I just need the thing in green, right? Like I just need the subject line, because the program doesn't depend on any of that, right? And so, but I only need it between 9 a.m. and 5 p.m., not outside. Right? So it's subject line between 9 a.m. and 5 p.m. And so what we did was like we realized that you can use a bunch of like standard PL techniques to analyze this program and actually infer this, that hey, this is the only amount of data that you need. And then we have a way to basically scrub all of that other irrelevant data away out from the input without changing the semantics of the program here. And so the idea here is that the trigger service is releasing minimized data. And so if anything goes wrong, at least minimized data was released, not all of the data. Okay, so you can.
Just for example, the trigger API could have run the program itself, found its output.
Hopefully, yeah, but running this, so like they are just APIs, right? It's just get and put data. It would be nice if they did that, But then they have to okay, what language is this written in? Say it's JavaScript. Then they have to run a whole JavaScript interpreter. Then they have to make sure that they have enough to run at large scale. Then they have to keep it updated in terms of security.
Here, what's happening? You do this thing on your side.
Yes.
So the Twitter API somewhere. This is in some standard language that it works.
Yeah, this program is in a standard.
I thought you're summarizing that program to get this thing.
Yeah, so we analyze this program to determine, okay, what parts of the trigger data are needed. And we do that on, again, our trusted client device.
Oh, that's not done by, the Twitter API still, how do you ask the API not to send us?
Oh, so that's a trick. Like what we do is, we essentially, we kind of almost like interpose on this communication here, and we just scrub out the parts. We replace them with nulls basically. So the same data packet is being sent, except that there are nulls everywhere else.
So you're saying that's a much simpler program than actually running.
Yes, yes. Yeah, I mean that's a lot less data that's being transferred out from the trigger
So
side.
then you put in the middle, that's running some computation.
Yes,
Because
yes.
after computation, I might as well have run the
You could have just, yeah, but that's not what it is. Yeah, yes.
Kind of feels like the kind of intelligence we're talking about is.
It is fairly simple, but then still, like, running all of that, like all of this is written in JavaScript, and then you have to support a whole JS interpreter if you want to run all of that in the trigger or in the endpoints. Sorry?
Just compile the program and put it in the
You, what do you mean?
Make whatever logic, don't put it in JavaScript.
Mhm.
Put it in your simple language.
Right. So, so the reason this is, so yes, I mean, you're using a subscript or JavaScript, but the reason they use JavaScript is because they want, they want the full power, right, of doing whatever JavaScript can do at some point. Right now, just empirically, we are observing that they are using very simple programs, but over time, we have seen
No,
that
I'm
they are
saying
becoming.
Just make a compiler and make it into a more standard form. So
Yeah, but then even then, you have to run, you have to isolate these binaries from each other in the server, in
not
the.
binaries, I'm saying in a standard form, like a structure. If this predicate and the way you are defining it, instead of like having to do a JavaScript. My issue is that the logic for saying I want to take these fields and write down this field is almost as complex as
Oh, you mean the logic to kind of nullify that stuff? Yeah, but that's fixed, right? I mean, we are just looking at a JSON object, and we're saying, okay, out of these JSON objects, you filter everything except these three. That's a fixed logic compared to like here, this transformation here could be any number of JavaScript statements doing whatever the user wants to do.
you can handle loops and everything in your program.
Yes,
So you are
Yes.
for that.
assuming we can unroll them to some extent. Yes.
So maybe you should still have not got to your stocks.
Okay, so what I'm going to do is, so I'll just talk about, so a few years ago I led this project where we were doing, what we call physical adversarial examples. And the idea is that, say that you have a self-driving car, it's going to use a camera to detect things on the road. This is kind of clean stop sign, and that's kind of the result of an attack with a few stickers on it. And this is kind of the result of a machine learning model at the top, that is running on these videos. And the idea is that just with a few stickers, you can completely change the perception of the machine. And this is important to understand because, how are you going to hack a car, right? You can, okay, I hacked the computers, but then if I have hacked the computers, I don't need to worry about, hacking the machine learning. I have hacked the car. If I just want to control a self-driving car by hacking the machine learning, the most reasonable threat model is to attack its perception, right, of what it is seeing in the real world. And so we had an algorithm to kind of, compute those stickers for different kinds of machine learning models, and kind of, cause these kinds of attacks to happen. Now the thing is, that's all good. But it's not the whole. It's not a satisfying answer to the question of whether you can hack a self-driving car in the physical world by manipulating its environment, because you know, a real car is, again, it's a system, right? I mean, you have your model in there, but then you have a bunch of other things. You have you have all of the traditional control, you have all of the sensing and the signal processing, you have a lot of things kind of going on in there. And so the goal is to kind of, understand, like, from an end-to-end perspective, can these attacks have real effects? Okay. And so because of questions like that, we come up with many questions that we are trying to answer. And I just want to highlight, one thing here, which is, we did this work on, like, putting these stickers, and they're kind of super visible to human eyes. And since then, everyone has been doing attacks of this nature where the attacks are very super visible. But is that an assumption that needs to exist, right? Does it always have to be visible to a human being? Is that an assumption? Is that a true assumption or a false assumption? Okay. As it turns out, it's actually a false assumption, right? Okay. You don't actually have to be visible to a human to trick these models. So here is an example where we can essentially manipulate the light that falls on an object, by hacking a smart LED. But then because of this rolling shutter effect in most digital cameras, you can actually control the flickering of the light in a way that a human cannot see, because biologically it's impossible for us. But then the machine is going to see that because of the rolling shutter, and then that pattern can trick the machine learning model. Okay. So this is, again, this work is kind of very different from the systems work that I tend to do. But again, taking this kind of the systems perspective leads to all kinds of interesting questions. Okay. I'm going to skip over this process of how we did it. But to answer your question, the stop sign thing that we did, there was a lot of impact. A lot of people kind of spoke about it in the news and all. And then the Science Museum in London, this is one of the largest science museums in the world. They were interested in acquiring the artifacts we use in our experiment for that video I just showed. This is an attack on an object detector, but same idea. And this is actually a photograph from the stuff on display in the Science Museum. So, I started out the talk by talking about, I'm interested in impact beyond, you write the paper, good for you, but beyond that, you want to do something. And these are just one example that turned out that way. Okay, cool. So hopefully I've kind of made a case for kind of thinking of security as this end-to-end thing where you look at all layers. And I'll just leave you with this. I'm looking to hire students, postdocs. UCSD is a very good place to do security research. So if you're looking for something like that, you should chat with me. So yeah, thanks. Thanks.
Meeting is being recorded.